Welcome everyone to this week's lecture on recurrent neural networks. So let's recap what we've done so far. So we learned how to get a numeric vector representation for single words in isolation. But we used n-gram to do that. But as we've seen, language needs a lot more than just single words next to each other because context provides a lot of information as to what the speaker is trying to convey. So the context surrounding words is very important when developing an NLP model. Now, for simple tasks like part of speech tagging, we can, go on with a small fixed size window. Maybe just 5 words is sufficient, as we've seen, because that provides sufficient context to figure out what part of speech a word represents. But that's not enough to develop an NLP model. So more complex tasks like question answering or reference resolution will require much longer context. Okay, so for example, a nice sentence in your book is, Eduardo told me that Miguel was very sick, so I took him to the hospital. By the time we reach the word him, to know that him refers to Miguel in that case and not Eduardo requires context that spans from the first all the way to the last word in the sentence, which is a 14-word context. So, as you can see, just extending the number of words in an n-gram model is not going to be realistic. So that's where recurrent neural network help in this case. So remember that the language model essentially boils down to a probability distribution over sequences of words. So essentially what we do is, using this probability distribution, is to guess what is the next word in a text given all the previous words. So it's a conditional probability distribution given all the previous words that we know so far, what is the most probable word next. And we're going to build on this idea, but what we need is a way to essentially convey information about the previous words and not just limit ourselves to a fixed context window. So because running an n-gram model or even a feed-forward network with a fixed window will face problems, either because we will need context that extends beyond the fixed size window, or we're going to end up using a window that's so long that we're going to end up with a model with way too many parameters. So in an RNN language model, each input word essentially will be encoded to start with a word embedding vector, xi. Now we're going to look at this as a time series of words. So each word will treat it as a time step essentially. Okay, because if you remember when we introduced recurrent neural network, we use them to process time series data, one data point at a time. So if we use them in processing language, we're just gonna use them one word at a time essentially. Same idea, but instead of time steps, it's gonna be word by word. So each word will be represented as a word embedding vector xi, and we will have a hidden layer zt, which is a hidden layer at time step t, which gets passed as input from one time step to the next. So we're interested in doing multi-class classification, So the classes are the words of the vocabulary. So essentially, we also want a probability distribution over the words in our training corpus. And also, we're going to end up sampling this distribution, or maybe picking the word with the highest probability to determine what word comes next. So the output yt at any given time step t will be softmax probability distribution over all the possible values of the next word in the sentence. Now the number of parameters in the weight matrices will stay constant, and weights will be the same for every word position. So let's look at a diagram showing how the RNN works in that case. So each input xi is a word embedding vector, and the output at so x1 is the first word in the sentence, the vector representing the first word in the sentence, and then you have y1, which is a word that comes after x1. So essentially, the true y1 is x2. So the sequence y1, y2, y3 is the same sequence as x1, x2, x3, except shifted by one word. Okay, so there's no y0 essentially. So at each time step or at each word, we're trying to predict the probability distribution for the next word. So as you can see, at each time step, we're passing the hidden layer as an input to the next layer. By doing that, essentially, we're carrying over information from earlier in the sentence into later in the sentence as we train this network over different time steps. So RNN architecture then will help us solve that limited context problem, because in theory there is no limit as how far this network can extend, right? As long as the sentence keep going, we can keep carrying over this information from one time step to the next. So each update of the hidden layer ZT at any time step T will have access to two things. First, the current input word at that time step, and the previous hidden layers ZT minus 1, which itself carries information from all the previous hidden layers that came before it. So this means that the information about any word in the input sequence can be kept in the hidden layer indefinitely, copied over from one time step to the next. Now, obviously, there's a limit to the amount of information that the hidden layer Z can carry. So at one point, it's going to start forgetting about what was said earlier in the sentence and give more weight to more recent words, and we will have to deal with this problem later on. So in practice, this architecture here for the recurrent neural network performs very well on many tasks, but not all tasks. So really, to know whether or not it will work for you on a given problem, you have to try it out. One factor that helps the success of the training process is that the network learns what information to keep as the sentence is processed during training. So that's very important, is that it's not up to us really to say the context is 5 words or 10 words. The network itself decides what part of the input is useful to remember for later on. So, like I said, to train this network, the input xt are the words in the training corpus of the text, and the observed output are the same words offset by 1. Okay, for example, let's say one of our training sentences is hello world. So x1 will be hello, and the target y1 will be the word world. And then to calculate our loss, we will compare the probability distribution we got for y1 to the true word, which is world, which we were hoping to get. So by computing the difference between the observed output, y1 hat, and the actual output we were targeting, which is the word word in that case, we can calculate the loss, and then we can do backpropagation through time to minimize that loss function. Now, once the model is trained on all the sentences in our corpus, so our corpus is going to be very large, of course. Okay, so it could be the entire text on Wikipedia, or in reality, it's millions of sentences. So, but once the training is done, we can then generate any sequence of random text we want. All we have to do is just provide the first word of a sentence, x1, and then the network will give us all kinds of predictions for y1, y2, y3, and so on. The book has an example for a recurrent neural network that's trained on Shakespeare text, and you can see that the generated sentences conserve a style similar to what you would expect from Shakespeare text, essentially. So depending on what the network is trained on, the probability distribution will adjust to reflect that style. So we can then use this network once it's trained to generate sentences as long as we want, given the starting word of a sentence. Just what we do is, after every time step, we sample the probability distribution to get the next word given the previous words. Okay. Now you could simply select for the next word, select the word with the highest probability. That's straightforward. Or you could just use a random number generator to sample the distribution based on that probability distribution, so that gives some variability. Or you could even inject your own oversampling to try to get some less likely words in your sequence that you're generating, just to add some variety to the output, so you don't keep getting the same high probability words over and over again. So these are different ways to generate sequences from a recurrent neural network. Now we can also train this network to do part of speech tagging for us. So in that case, we're going to need some training data, because we can't just use the sentence and then shift it by one stop to get the output. So what we would need in that case is essentially a tagged corpus with sentences with each word in the sentence tagged with the correct part of speech it refers to, and then that would be our Y target that we're trying to train the network on predicting. Okay, let me continue in the next video.